2nd, 2025. Thank you for joining me on Modified Weather Watch. Today's focus, we're going to be discussing persistent contrails. Is there even a such thing as chemtrails or chemical trails? I think it's not a surprise by now that you guys do know the positioning of this channel and what it stands for. But the point of this is to show scientifically what is going on up there in the atmosphere with this. So it is a little bit more academic driven. However, if you still are an avid weather enthusiast, I do encourage you to watch it and follow along with me here. What I'm showing first is the long wave infrared window. What we're looking at is the temperature of the cloud top heights. I have the legend on the left column here. And we're going to focus on the Celsius side. And I want us to focus on southern Illinois because that is where the previous slide contained those contrails that were laid down. Let me get my pen out here. So we're watching across this area, and this is where I want you guys to focus across the entire video. For the purpose of what's going on outside of these of southern Illinois, we can see cloud top heights across Iowa and Nebraska reaching somewhere around 45 degrees Celsius. So as a meteorologist, I'm looking at this, I'm analyzing, and we can deduct that these are mid-level clouds. These are likely cumulus clouds because they're able to tower up and reach that high up in the atmosphere at about negative 45 degrees Celsius. We look over here into eastern Ohio, western Pennsylvania. We see the cloud top heights. We're talking probably negative 14. There's some pinks in here, purplish up to negative 20 Celsius. So that's how we're reading this, so we can see the clouds or the contrails that are showing up across southern Illinois are showing up here at about negative 14 to roughly negative 11 degrees Celsius here. This is crucial. If there's two things I want you to remember, it's the level that these clouds are, the temperature, and this color overlay. So we're in Celsius. Please do not forget that, guys. This is the most important piece I want us to remember across this video. Let's set the stage synoptically what's going on. There is a high pressure that's sitting over Missouri. Oftentimes around high pressure we get clockwise flow, anticyclonic flow is what that's called. And we can see that with this. Notice that the clouds are actually riding around the cusp of this high pressure system. That tends to happen because this is very stabilized air in here. It's very hard to get cloud formation. Another thing I want us to note is because this air is spinning clockwise, these contrails are also going to have a little bit of a clockwise rotation to them, a rotational component. So let me go ahead and clear this out. If we lay a trail like this and we introduce this into high pressure, that clockwise flow, if this trail is laid here at t equals 0, maybe, I don't know, we could say arbitrary here, about 3 hours later, this same trail may be slightly more tilted, so it's like that. So we get a little bit of that clockwise torque, clockwise rotation out of that, and that does happen across these trails that were laid in southern Illinois. Okay, here's a closer look at it. Again, most important piece, these cloud top heights are occurring. They're registering at just under 15 degrees Celsius, negative 14 to negative 11 Celsius. Most important thing to remember. Again, I'm going to repeat that. Here's a look at the low-level water vapor, and we can see this is creating an anomaly in the water vapor. Well, because once these jets let and release out their payload, that does contain water vapor, and this is creating an anomaly. We see this show up in low-level water vapor imagery. The yellows are drier air. Anywhere where we see these blues, that is more low-level saturation. So these are showing up as an anomaly in terms of water vapor imagery. Here is a look at simple RGB water vapor. We're combining all layers. This is just very useful to get a general look at what type of cloud we're looking at. And again, we can see these are more low level. These are lower level stratus clouds. They're stratiform clouds. These are not being sprayed up in the cirrus layer. And we'll get into that here in just a second. Now let's extrapolate this even further, and I'm going to highlight some of the most notable trails. And what you'll notice with this is this does follow an advection pattern. Advection is the horizontal transport of air. Our convection is the vertical, advection is horizontal. And we can pick out, before I get ahead of myself here, this exact frame, this image is that ground verification. So where I'm standing from the ground underneath, this is aloft what it looks like if we're in space. This is what was showing up on that imagery. But anywho, here we see that we have a geometric configuration in which these are allowed to advect across the region. And I want to question you guys and open up what passenger jets would make this kind of configuration. This is something that would require the utmost timing and calculation in order for these to intersect each other and also move congruent and remain equidistant to each other and advect all as one large unit. So again, I lay it out and we can see this does have a set pattern. And I even flash this so we can see that. There's clearly triangles that are formed by these contrails that advect in a pattern. So let's get into now more of the technical stuff. And here again, this is what it looks like. That's that ground verification. We can clearly see this here, how this shows up. And this does play a role on solar radiational budget. So if this trail weren't here, technically there would be more sunlight reaching the surface underneath it. So, all right, let's get into the technical analysis. This is the most crucial aspect with this. Unfortunately, I don't have an actual observed sounding where we're launching a radiosonde with a balloon, so we have to use high-res modeling. This is the HRRR model. I used this about roughly 7 to 8 hours prior to this event happening. So this forecast here at the time I pull this sounding is looking at about 7 hours in the future. So it's fairly accurate. It's not a perfect 100% correlation because this isn't sheer raw data that we're actually observing by putting a balloon up into the atmosphere. But let's break this down and dissect this. We see these cloud top heights are reflecting at about -14 to -11 degrees Celsius. And on our skew-T sounding, what I'm looking at is this is where this is occurring in the atmosphere. This is our dew point, so this is our saturation, this green line. Our temperature is in this red line. We want the green line and the red line to be as close as possible to have more saturation. The further apart we see these from each other, the less likely we have saturation. So notice there's more saturation closer to the surface than there is aloft where I'm looking. Where I have this yellow line intersecting up here, so this yellow line out here, this is occurring at about 5 kilometers in height. So our height axis is on the y-axis, and we actually have a slanted temperature axis that runs like this on a skew-T. I'm not trying to break down the logistics of what a skew-T diagram is, but I'm showing you guys as a meteorologist when we're looking at soundings that these cloud tops are possible. We get cloud formation. If this is happening at about -14 to negative degrees Celsius, this is the only possible layer that these clouds can form at because this is where we have the greatest localized saturation in the atmosphere. We can't get cloud formation out here. We could get it up at 9 kilometers, but we don't see that show up. If we had this at 9 kilometers, these cloud top heights would be much, much colder. But they're not. These are much warmer, so they're going to show up at -15 degrees Celsius. So I'm showing you guys that in this white circle, this is where that saturation has to be in order to get these clouds to form. So maybe this model is a little bit underdoing its saturation, but let's go ahead and calculate this in more of a technical sense now. Again, here's that closer look of this. We see these cloud top heights are occurring at -15 and just below that. Because look at this actually. We see some of these pink clouds pop into Missouri. So we can literally see that, okay, some of these cloud top heights have grown a little bit. This is -20 Celsius right out through here, but we don't get that out here. We stay just under that -15 Celsius. This is why this is crucial, guys, because this is total crap. The Smith-Appleman or Schmidt-Appleman, whatever you call this, for contrail formation, it's a total lie because here we are, we convert -13 Celsius to Kelvin. That's 260 Kelvin. So we're sitting right here. Here's 260 Kelvin. I've extrapolated this silly little graph. And according to this silly little graph, we should never get contrails. Well, they're right here. We have contrails. This is incorrect. It's false. It's false. So let's go even further here. Also, we're looking at 5 kilometers here. This is where 5 kilometers occurs. So I'm putting this together. This is our atmospheric conditions, and you're going to tell me we can't get contrails. That is incorrect. So next, what we have to do is calculate the saturation vapor pressure. What is our relative humidity? Let's debunk this silly little graph as well. Again, our temperature in this case, 13 degrees Celsius. That converts to 261 Kelvin. I'm doing the work for you guys. We're going to calculate the saturated vapor pressure. Its units are in hectopascals once you solve and plug in for your equation. And then when we get our humidity, we simply take our vapor pressure over our saturation vapor pressure. But here we go, guys. I've plugged in all of these numbers into the equations. This is our saturation vapor pressure. This is our vapor pressure. I'm putting into T for this. This is the temperature. Our temperature is -12, and this has to be converted into this stays in Celsius, excuse me. So these stay as in Celsius. That's the conversion. I put this right in through here, and we get these spitting out. This E is 0.88 hectopascals. Saturation vapor pressure is 2.44 pascals. So when we use this, we can get that ratio. We divide the vapor pressure by the saturation vapor pressure. We get a 36% RH. So we have contrails forming with 36% relative humidity. But how's that possible, guys? This graph tells me we can't have that. How's that possible? 261 Kelvin is all the way out here. Our saturation vapor pressure, it's off the charts. So how is this possible? I can tell you how it's possible. We have to figure out what chemical properties or agents are used to promote this formation. It's helping to enhance and lean into what available moisture we have in the air. So we're going to get that formation. Let's quickly break down the chemical composition of the atmosphere. Primarily nitrogen. We've got oxygen, argon, and small amounts of water vapor. I'm going to show you guys that if we spray something like a barium salt, BaCl2, that will latch onto the water vapor. You get barium chloride dihydrate. This is a toxic, it's a crystalline solid. They're ice crystals. In the chemical term, it's known as an acute toxic, as an irritant. But this is what happens when you put barium salts into the atmosphere. It's going to latch on to the water vapor, and you get this chemical composition. So what I want us to take away from this, guys, just because we have 36% relative humidity does not mean we cannot get cloud formation. If we're introducing BaCl2, barium salts, those aerosols will allow for to have water condense on it. So think of it as the atmosphere can hold on to as much water vapor as it wants to. If we're introducing an aerosol into that layer, it's going to latch onto that. And furthermore, barium chloride dihydrate and barium, elemental barium in of itself, it's hygroscopic. This will absorb moisture from the air. So we're going to remove the moisture that was in the air, and it's going to latch onto those aerosols that are injected into that atmosphere. So let's take a look here again real quick, courtesy of PubChem. What can happen with the implications of this? What happens if we're spraying these salts, barium salts, in the atmosphere? Well, this can cause cough, sore throat, redness to the skin, even abdominal pain, nausea, diarrhea, vomiting. Notice how many of you guys have sinus problems out there. Are you congested? These are some symptoms that can be as a result of spraying this. So to summarize, guys, I'm proving to you that we do have these. They're sprayed at -12 Celsius, somewhere around there, give or take a couple degrees Celsius. It's approximately 260 Kelvin. We convert this. We can, in fact, figure out that this is occurring at about 5,000 meters. It's not where commercial airplanes fly. And in doing so, by spraying this across southern Illinois, we're changing the solar radiational budget. We're changing how much incident light is reaching the surface. This is going to enhance and modify our jet. Guys, that's all I have for this video. Please share this. We need to open up these conversations. It's really easy to debunk these things. It's right here. I've done the work for you guys. I've done this for you. It's up to you. Please show this to people. Academically, we need to challenge this stuff. It's right in front of us. I'm not sure what meteorologists are doing here, but I'm telling you, this is what is going on right now, and it's atrocious. No one seems to really be talking about this. We gotta start bringing this out and talking about it. Thank you guys. Take care. God bless.